Okay, so in this lecture, we are going to introduce the concept of a ring. Okay, now rings are basically rings are you can say it to be a structure induced by groups. Okay, what do you mean by this statement? Is that we get hold of a group and using the structure of that group, we form what we call a ring. What we typically do is that we consider a non-empty set, a non-empty set, say R, okay, and we consider two binary operations and two binary operations precisely, which we denote as plus and dot, okay, such that R with respect to plus is an abelian group, and R with respect to dot is a semi group. That is, it's just closed. The operation dot is just closed over R, hence we call it a binary operation precisely. It's associative. That's precisely what I want to say. Okay. Then we say that R with respect to both of these binary operations form a ring. Okay, clear? So what we are essentially doing is that we start with an abelian additive group and we introduce another binary operation to it such that with respect to the new operation, the set is associative and closed. Then the structure with respect to these two binary operations as well as the set obviously is called a ring. Now rings are very, not studying rings is a very rich and elegant topic. It has variety of applications like we need to study polynomials, roots of polynomials and the algebraic properties of polynomials, and to do that efficiently what we need is called a field. Okay, and the notion of a field is somewhat induced by the notion of a ring. Moreover, there are very important structures which precisely resemble the concept of a group action. Typically in this case it's called modules. Okay, so in a way, like we had studied group actions, we will also study something called ring action, which has precisely the terminology modules, and that's a very fine and a very strong topic for advanced algebra. Moreover, if someone wants to get introduced to the concepts of algebraic geometry, then also ring forms an introductory topic to that. Okay, so it has variety of applications. So this is the mere definition of what a ring specifically is. Now there are more structures which we can give to a ring. Firstly, if R is commutative with respect to the operation dot, then we say R is a commutative ring. And studying commutative rings typically forms a class of algebra which we typically call concepts of commutative algebra. Okay. Number two, if 1 belongs to R, where 1 is such that for all A in R, A multiplied with 1 is same as 1 multiplied with A is same as A. That is, we are talking about a multiplicative identity for R. That's what we precisely want to say. If 1 belongs to R, then we say R is a ring with unity. R is a ring with unity. Rings which are both commutative as well as has unity are also very important for studies. Okay. Specifically, when we talk about modules, we on a while studying commutative algebra, the rings which we usually consider are the ones which are commutative as well as which contain unity. Okay. Or it's often called ring with identity as well, whatever. Okay. Third one is sort of which is the I feel at least in this case is one of the most important parts of algebra, which is that if for all zero non-zero elements from R, there exists an element B from R such that B is also non-zero, should precisely, or let me just write B, okay, it won't make any difference as such. B in R such that AB is equals to BA is equals to 1, then R is called a division ring. R is called a division ring. And uh, a ring R which is all 1, 2, and 3. That is, it's commutative. It contains unity as well as it's a division ring. Is what we call a field. Okay, that's precisely the definition. Moreover, in this case, in part 3, this element B is specifically, it's denoted as A inverse. Like these are things which you already know from group theory, these symbols and these cases. One second, let me just decrease it out. Yeah. Okay, clear? Okay. One more thing, I should just conventionally, or I shouldn't use the term conventionally. I should use the term precisely, and this is easily observable precisely for all non-zero rings. For all non-zero rings, non-zero rings in the sense that if a ring contains only the zero element, only the additive identity, zero precisely means the additive identity, and one if exists in the ring, it's precisely the multiplicative identity. So if I am not talking about a zero ring, that is a ring which contains only the zero element, only the additive identity. You can obviously observe the fact. Okay, first let me write it out. What I'm trying to explore actually. Let R be zero, just the zero element. Then you can observe that all the axioms of ring are successfully satisfied. Moreover, R actually forms a commutative ring as well. In fact, it also forms a commutative ring with unity as well. Precisely, right? We're not talking about it being a division ring because there are no non-zero elements. So that's not something which we want to discuss. But precisely the fact is that R is a commutative ring with unity, right? And what is the unity in this case? It's precisely the zero element. Because if I choose the zero element from R, then for all A in R, where A is exactly nothing but zero, A dot zero is same as 0 dot A is zero, but zero is the only element A. Right? This sort of seems to be a bit confusing, but if you carefully observe it, what I'm trying to say is that in this case 1 equals 0, where 1 denotes the multiplicative identity and 0 denotes the additive identity. So if I choose any non-zero ring for non-zero rings, 1 is never equal to 0 if exists, obviously, if exists. That is, the multiplicative identity is never equal to the additive identity at all, at any cost for a non-zero ring. In case of a zero ring, it is vacuously true, right? There's nothing to talk about. So whenever we will be talking about non-zero rings, precisely the thing is that the multiplicative identity is never equal to the additive identity, because it will lead to, very absurd results. Yeah. So let's continue our discussion. Um, Now the first question which should arise is that why is the ring, it is needed to be abelian with respect to the additive operation. Now the fact is that, like, we are defining the rings in such a way that we can impose some extra structures on the ring to get some more elegant structures out. For example, a simple ring might not be as useful as a commutative ring or a commutative ring with unity, or in fact a field. The fields are the most important ones, which you will get to know if you do a course on field extensions and field theory. So a ring, a simple ring, the definition of a simple ring is sort of a general case, right? Where we can impose different restrictions to get some different structures, which are sort of more useful. So suppose I say that one is in R. Suppose R contains the additive, the multiplicative identity. Then observe that, suppose I choose the elements A and B from R as well. Then 1 plus 1 times A plus B, I can apply the distributive law. Okay, I have missed out the distributive law. I'm very sorry, I should have mentioned it. Since we are talking about two different operations, so I should be concerned about involving the relationship between these two operations as well. And that relationship is what we call distributive law. Okay, so I should just, so R dot is a semigroup and then R plus 1. If for all A, B, C in R, A plus B dot C is A dot C plus B dot C, and A dot B plus C is A dot B plus A dot C. So these are called the distributive laws. I'm very sorry I missed it out. These are called the distributive laws. Okay. Um, so these need to hold as well. That is, there must be a relation between the two operations which we are trying to use. Yeah, let's come back to what we are trying to discuss. So 1 plus 1 times A plus B. So I can distribute it in terms of the first element. So I can write it as 1 times A plus B plus 1 times A plus B. But then if 1 exists, then this is nothing but A plus B, and plus you have here A plus B, right? But I could have also distributed it in terms of A plus B. I could have also written it as 1 plus 1 times A plus 1 plus 1 times B. And then if I distribute it out, I get A plus A plus plus B plus B. But then if you carefully observe the fact that since the left hand sides are equal, the right hand sides must also be equal. But if the right hand sides are equal, then A plus B needs to be equal to B plus A. So in a way, the ring to be abelian in terms of the addition operation is sort of forced. Okay. Okay. Yeah. Now let us structurize some examples. Examples. Number one, what this is what we call a trivial ring. Okay. What is a trivial ring? You consider any commutative additive group. Consider an abelian additive group. Okay. G. Define an operation dot on G such that for all A, B in G, A dot B is precisely 0. Okay, clear? Then G plus dot is a ring. Okay. Moreover, if G is 0, if G is just the 0 set, then it is indeed what we call the 0 ring, which we had previously discussed. Clear? Now there are variety of definitions which are pretty easily justified. For example, if I consider Z with respect to plus and dot, where plus and dot both are your usual arithmetic addition and multiplication, then you can easily observe that Z plus dot is a ring. In fact, I can say something more. In fact, it's a commutative ring with unity, right? The usual multiplication in terms of integers are commutative, and one, the integer one, it acts as the identity, multiplicative identity. Okay. Moreover, can I say that it forms a division ring as well, right? So surely it does not form a division ring. The reason is pretty obvious, because if I choose the element 2 from Z, suppose 2 has a multiplicative inverse. Suppose 2 times some element A is equals to 1 in Z. But that would imply that A is equals to 1 by 2, but 1 by 2 is not an element of Z. So clearly enough, the set of integers does not form a commutative division ring. Does not form a commutative division ring. At least a division ring. But you can surely observe that Q with respect to usual addition and multiplication, R with respect to usual addition and multiplication, C with respect to usual addition and multiplication, all of these form fields, because they will have respective inverses as well for every non-zero element from them. And the identities obviously exists as one. The one element, the element one is obviously the identity in all these three cases, and they are all commutative with respect to usual multiplication, right? So this is a very trivial observation. We're not going to discuss such things here. But the third example is sort of important. Consider the ring Zn with respect to usual addition modulo n and multiplication modulo n. So this is your usual addition modulo n, and this is your usual multiplication modulo n. Okay. Now Zn with respect to plus, it's surely a group, and Zn with respect to dot is surely a semi-group. These are obvious facts, right? And moreover, thus simply this is a ring structure. This structure is simply a ring, right? Now the problem which I actually want to discuss here out is that I mean, see, this ring is actually a commutative ring, because multiplication modulo n is commutative in nature. Moreover, Zn contains the element 1, and 1 surely acts as a multiplicative identity, right? The question is that, can I talk about inverses of every non-zero element? Okay. Now, if you recall the study of the group of units, which I had covered in my lectures on group theory, there we had discussed the fact that to ensure a multiplicative group out of the elements from Zn, I must consider only those elements where n is, I should use the term k, let's say, where k is non-zero coming from Zn, such that k, the GCD of k and n is 1. Okay. Only then we have the surety that every element k will have a multiplicative inverse, where the operation is basically multiplication modulo n. Okay. So for Zn plus and dot to be a field at least, or a division ring, commutative division ring, I need to get hold of n in such a way that every element in Zn Zn minus 0, because when we are talking about inverses, we are not including the element 0. So every non-zero element from Zn, they have inverses. For them to have inverses, they need to be co-prime to it. And when we can ensure the fact that every element coming out from every non-zero element coming out from Zn is co-prime to n, if n is a prime number, right? Surely Zp is a field. Or you can write it in this way, that Zn is a field if and only if n is clear. Okay. Now let us discuss a few important examples. I'll discuss a few elementary examples in this lecture, and in the next lecture we will be completely focused on exploring some highly important examples of rings, which require a bit of, I should say, a bit of complicated thoughts. The only complicated example I will be considering in this lecture is just various types of rings where it's not mandatory for the ring to consider a unity or it to be commutative, and so on and so forth. That sort of concepts. Like we already know that all rings need not have, no, I mean, all rings need not be division rings. Like for example, Z was one of them. But the rings we have discussed till this point, they have they are at least commutative. So let us discuss a example of a non-commutative ring. A non-commutative ring. Okay. So this example, yeah, let me consider the collection H to be the collection of elements of the form A plus Bi plus Cj plus Dk, such that A, B, C and D are all real numbers. Okay. This set was provided by Sir William Rowan Hamilton, and I guess this was the first non-commutative ring considered as an example. I don't exactly remember. So I mean to say that this was one of the first non-commutative ring proposed to be existing, some sort of that. Okay. Now, how do we give the ring structure to it? What we do is that we use the component-wise addition. We use component-wise addition. Okay. So A plus Bi plus Cj plus Dk plus say P plus Qi plus Rj plus Sk. This will give you A plus P plus B plus Qi plus C plus Rj plus D plus Sk. Right. Clear? Okay. So this is the additive operation, and you can surely ensure the fact that H with respect to this addition forms a group, forms an abelian additive group. And this merely comes out from the fact, because since each A, B, C and D, and in fact the P, Q, R and S, they are all reals. So and the addition actually are happening in terms of the coefficients, right? In terms of coefficients, I mean these are considered to be the coefficients. These elements A, B, C and D. Ij and K are fixed. Okay. I will assign some values to them. You will get to know what they actually stand for. But so since these come from R, and the addition simply happens with respect to the addition on R with respect to these coefficients, and they will obviously commute, right? Because R is a commutative additive group. Hence, the commutativity is obviously justified. How do we define the multiplication now? The multiplication, is defined as, so what we do is that the multiplication is usually defined in distributive way. That is, we consider simple distribution of these two elements in terms of multiplication. For example, like we used to do in integers, right? Suppose we have A plus B times C plus D. So it was written as AC plus AD plus BC plus BD. Like, we are going to simply use that distribution. But we need to have something more. What we ensure is that I squared is same as J squared is same as K squared, and they're all minus ones. So they sort of resemble the iota, complex number iota. Moreover, they sort of also resemble the unit vectors in R3. Like, what we have is that I multiplied with J, it will give you same as J multiplied minus of J multiplied with I equals to K. Then J multiplied with K will give you same as minus K multiplied with J, and it will give you I. And then K multiplied with I will give you same as I multiplied with minus of I multiplied with K, and it will give you J. Okay. So what we are trying to do is basically you just remember this fact. I goes to J, J goes to K, K goes back to I. So when we are multiplying in this way, we get the element, the other element with respect to a positive sign. So I multiplied with J will give you K with respect to a positive sign. And if I just go reversing the arrow, if I go in this direction, then J multiplied with I will also give you K but with a negative sign. That's exactly what we are doing. So in terms of this, we can define the multiplication. Okay. For example, suppose I have the elements, let's say 2 plus 3i plus 6j plus 0k times say 1 plus 6i plus 0j plus 4k. So I just use simple distribution. So I get 2 times 1 plus 2 times 6i, so I get 12i plus 2 times 0j, I have nothing, so I have here I have 2 times 4k, so I have 8k. Plus then I do it with the element 3i. So 3i times 6i will give you 18, and I squared will give you minus 1. Right. So I will have minus 18. Then 3i times 0j will get nothing. 3i times 4k. So ik is minus j, and 3 times 4 is 12. So I get minus 12j. And in this way you can continue. Am I getting my point? Observe that this ring is obviously non-commutative, and it is simply non-commutative because ij and ji are not same. Similarly, jk and kj are not same. So when you are distributing from either directions, the ij and ji won't be same. So there will be different results if you multiply it from by reversing them out. Okay, this is very observable. Okay. Now this ring surely has identity, which is simply the element 1 plus 0i plus 0j plus 0k. That is very trivial to observe. And moreover, if I talk about any arbitrary element, say a plus bi plus cj plus dk, where a, b, c and d all are non-zero, or at least all are, sorry, I mean to say all are not zero. All are not zero. I am talking about a non-zero element. So for this element to be non-zero, all a, b, c and d need to be zero. So I am talking about all being non-zero. So I can define its inverse to be a minus bi minus cj minus dk divided by root over of a square plus b square plus c square plus d square. Clear? You can please do justify. Okay, clear? Now this ring is basically called the real Hamilton quaternion. So this ring is called the real Hamilton quaternion. You can also define the rational Hamilton quaternion by just fixing A, B, C and D to be elements from Q. That is to be rational. Okay. So let this lecture be up till this much. In the next lecture, we will be exploring certain properties of rings, and we are also going to discuss some other important examples related to rings. So meet you guys in the next lecture.